When we compare humans to the other great apes, we see that they have a rather unusual life history. These unusual features include large, fat, relatively undeveloped infants, early weaning and short interbirth intervals, slow development and extended childhood, usually one offspring, occasionally two, and menopause. We also have a life which is considerably longer than those of chimpanzees or bonobos. To see this concretely, let's take a look at two mothers. One of them is named Emma, the other is named Fifi. Emma had 10 children in 17 years. 7 of them survived, and her interbirth interval was 1.8 years. Her age at first birth was 31 years, pretty advanced. Her age at last birth was 48 years, unusually late. Her age at death was 88 years. Fifi had 9 children in 31 years, almost the same number, but it took her much longer. 7 of them survived, as did Emma's. Her interbirth interval was 3.9 years, more than twice that of Emma's. Her age at first birth was 13 years, much earlier. Her age at last birth was 44 years, not that much different from Emma's, actually. And her age at death was 46 years, considerably younger than Emma's. Emma is Emma Darwin, Charles Darwin's wife. And Fifi is one of Jane Goodall's chimpanzees at Gombe. If we expand that to look at the human life history in comparison with bonobos, chimpanzees, and gorillas, the things that really stand out are highlighted here in heavier type. Humans are heavier when they are born by almost twice the amount of bonobos and chimpanzees. They are weaned earlier. The female age at first breeding is considerably later. The average maximum lifespan is 2 decades or more longer, and the interbirth interval is relatively short, not that much shorter than bonobos, but considerably shorter than chimpanzees or gorillas. The fact that humans are giving birth to offspring that need more care, nevertheless are being weaned earlier, implies that in humans, child care is a social endeavor. One person alone, a mother alone, could not rear this many children this fast. Now let's start with the human life history at the beginning, which is the egg. This is an image of an egg in a follicle in the ovary. The first point to make is that at 3 months of development of the fetus, her ovaries develop with about 7 million oocytes. These oocytes are progressively eliminated, and by birth she has about 1 million of them left, having discarded about 6 million, and by menarche a few thousand are left. Evidence suggests that the defective oocytes are being preferentially discarded. We also know that about 60 to 70% of concepti are aborted in the first following menses. Many of these are not even noticed. It takes a fairly careful study to get that kind of figure. Evidence from Hutterite women who have recurrent spontaneous abortions suggest that the human female reproductive tract is discarding concepti that are immunologically deficient, either because the paternal MHC alleles are too similar to the maternal ones for the immune response to function, or to avoid inbreeding depression. So they appear to be discarding lower quality offspring. About 70% of conceptions that start as twins end as singleton births. This is something we've discovered since ultrasound became standard practice. All of these lines of evidence suggest that the human female reproductive tract has been designed by evolution to function as a quality control device, a selection arena. The zygote survives this, implants, and grows, and is then born. Size at birth sets off a whole series of trade-offs. Human birth weights range from 1 to 4.5 kilos. In length, human infants are 40 to 57 centimeters at birth. Human babies have larger brains and they are fatter than babies that are born to a similar sized chimpanzee or bonobo. Relative to adult brain size, human babies should have even larger brains at birth, but their growth is constrained by the diameter of the birth canal. Therefore, human babies continue brain growth and differentiation for a relatively long time after birth, up until about 7 years of age. This is related to the evolution of childhood and is a stage in our life history that is lacking in chimpanzees and bonobos. The average birth weight of humans is actually about 0.5 kilogram less than the optimal weight for infant survival. This is either the result of parent-offspring conflict or of the constraints of a narrow human birth canal. Low and high birth weight adversely affect survival, health, growth, and mental development. And among other interesting natural history observations, long, thin baby girls reach menarche about 6 months earlier than normal, short, chubby ones because they more than compensate with later growth. Human growth patterns are very interesting primarily because they differ between the sexes. Human growth is target-seeking and self-stabilizing. It is divided into 5 periods: infancy, which is from birth up until about 2 years; childhood, which is from 2 to about 7 years when the brain finishes growing; the juvenile period is from the beginning of puberty at about 10 years in girls and 12 years in boys, up until adolescence, which continues through to full sexual maturity, which is about 14 in girls and about 16 in boys. And then adulthood. And adulthood catch-up growth can continue in males up until more than 25 years of age, although most males stop growing as teenagers. The growth patterns are different in the two sexes. Childhood may be a feeding adaptation that allows shorter interbirth intervals with family support. The human adolescent growth spurt is uniquely large. Chimpanzees and bonobos do not have that kind of growth spurt. Girls look adult and have menses before they are fertile, and they can engage in adult roles without becoming pregnant for a year or two after they appear to be adult women. Boys produce functional sperm before they complete growth and develop adult appearance, so that is reversed between the two sexes. Men are slightly larger than women, possibly because of sexual selection. And women store more of their fat in thighs, buttocks, and breasts. Men are more muscular. So there is sexual dimorphism in humans that's pretty standard. To emphasize the differences between the sexes, here are the growth velocities, so the rate of growth with age for girls in red and boys in blue. You can see that girls hit their peak growth velocity at about 12 and boys at about 15. So they are differing considerably in the ages at which they achieve biological maturity. Human patterns of reproductive investment are interesting. The proximate factors that affect fecundity and interbirth interval include nutrition, stress, marriage patterns, breastfeeding, contraception, venereal disease, conscious decisions, and the presence or absence of the father. All of those will affect interbirth interval and fecundation. Ultimate factors affecting fecundity and interbirth interval, the evolutionary selective forces, include offspring survival rates mediated by disease and nutrition, the presence and absence of relatives and mates who help with child caring. So this presence or absence of relatives and mates is something that developed evolutionarily as part of human social life, and it is probably on the order of 6 or 7 million years old. Mothers' fertility rates are trading off with infant survival, and that is shaping interbirth interval. Short birth intervals endanger children who are at both ends, because then there's going to be an overlap of parental care between the infants. Large families impose costs on 2 to 4-year-old children, and lactational amenorrhea regulates birth spacing to a certain degree. As long as a woman keeps nursing, she is less likely to ovulate. One of the interesting patterns of reproductive investment in humans is twinning. Here are some identical girl twins and some identical boy twins. 4% of births are twins. Twinning does pay in some environments, but not in others. It is more likely to increase fitness if both twins are girls. In food-stressed populations, twinning is maladaptive and it can be associated with infanticide, which has been observed in hunter-gatherer populations in both South America and in Africa. Ultrasound shows that about 70% of conceptions that start as twins end as singleton births, and that's another indication that twins are expensive. It's almost as though, oh, we made a mistake, we need to get back to 1 rather than 2, and one of them is resorbed. One study of twinning, done by Virpi Luma and her colleagues, showed that the Finnish archipelago had a richer and more stable food supply than the Finnish mainland in the 18th and 19th centuries. They found that twins in the archipelago produced more than 1 adult, but twins on the mainland only produced 0.7 adults. Twinning was more common in the archipelago, so the pattern seemed to fit the survival probabilities. Twin sisters were most successful, twin brothers were least successful. Mothers of twins had higher mortality after age 65 because they were more susceptible to tuberculosis. So a study like this shows that there are trade-offs between offspring number and the sex of the offspring and the adaptiveness of having twins, and also between offspring number, offspring survival, and parental survival. Now, what about sex allocation, which means the ratio of female to male offspring? In terms of cultural effects, we know that bride price societies limit the number of sons because sons become expensive when they marry. Dowry societies limit the number of daughters because daughters become expensive when they marry. Where sons inherit, the wealthy favor sons and the poor favor daughters, and that seems to be true in the United States, Hungary, and in Germany. That would conform to the Trivers-Willard hypothesis, which basically states that women in good condition should have more sons and women in poor condition should have more daughters, especially in any mating system in which the sons need to be in good condition in order to marry and have offspring. But overall, if we look across all of the studies that have been done, the support for the Trivers-Willard hypothesis in humans is really rather mixed. It's about 50% of the cases supported and about 50% do not. Now, what about lifespan and aging in humans? That we live longer than chimpanzees and bonobos might be the result of lower extrinsic mortality rates that are caused by our social organization and our group defense against predators. You can think of that as self-domestication. That effect, however, is not large enough to explain our observed lifespan. In addition, we may have to invoke intergenerational transfers, that is, parental care and cooperative child care, mother and father effects, and grandmother and grandfather effects, all of which increase fitness contributions of older individuals. So selection will act to extend lifespan if older individuals are having a greater beneficial impact on overall fitness. Now, men can reproduce later in life than women if they have several marriages in sequence. Women will stop with menopause, but men can keep going if they can then marry a younger woman. So selection to prolong male life may then indirectly prolong female life because many of the same genes and regulatory networks are involved in maintaining both sexes. That would not explain why women stop reproducing at menopause. So menopause is a bit of a puzzle. After all, in evolution, fitness is determined by reproductive success, and here women are stopping to reproduce. Why does that happen? We know that chimpanzees do not have menopause. Healthy females continue to have offspring right up until they die, whereas in humans, menopause is normal. There are at least 5 non-exclusive hypotheses for the evolution of menopause. As you'll see, we don't actually know which or what mixture is correct. The first idea is that it's about mothers. Mothers stop reproducing because the risk of dying in childbirth rises with age, and the mother must survive long enough to rear a child. There's no point in trying to reproduce if the risk is so high that you'll die and then the child will also die. The second idea is that it's about grandmothers. Grandmothers can better help daughters rear grandchildren if they do not have children themselves. Intergenerational transfers can increase fitness contributions of older individuals. So the grandmother hypothesis really takes as an assumption something like the mother hypothesis as a starting point. Third, it's about reproductive conflict. Mothers-in-law are more related to their own offspring, all 0.5, than to those of their daughters-in-law. They are related there 0.25. Whereas daughters-in-law are unrelated to their mother-in-law's offspring, 0.0, and they are more related to their own, 0.5. That means daughters-in-law are under greater selection to, quote, win conflicts over resources used for reproduction, and that could select against continued reproduction in older women in a fairly tightly knit society living in small groups. The fourth idea is that it's about offspring quality, essentially. Menopause is there seen as a byproduct of selection for an efficient filter to eliminate defective oocytes. It occurs when the supply of oocytes is exhausted by atresia. This works if enough improvement in offspring quality early in life more than compensates for reproduction which is lost late in life. That fits fairly well with the evolutionary theory of aging, but we have no direct evidence on it. And then finally, menopause is thought to be about self-domestication. So the idea here is that our social behavior, our agriculture, our culture, improved survival, extended lifespan, and extended post-reproductive life, but did so without increasing the supply of oocytes. Selection then modified the behavior of post-reproductive individuals to enhance their fitness by having them help to raise grandchildren. So this actually combines the offspring quality hypothesis with the grandmother hypothesis. The evidence is mixed. The mother hypothesis, the idea that mortality in childbirth increases with age, only works as a standalone explanation if the increase in mortality is implausibly large. There is some evidence for and some against the grandmother hypothesis as a standalone explanation, but it does seem to work in combination with some of these others. Reproductive conflicts between mothers-in-law and daughters-in-law appear to be real, and they could contribute to the explanation, but we have no quantitative measure of their effect. There is as yet no convincing evidence on the offspring quality hypothesis. It's logically plausible, but empirically unconfirmed. The self-domestication hypothesis is also plausible, and it rests on evidence for both the offspring quality and the grandmother hypotheses, which it combines. These hypotheses are not mutually exclusive, and some studies find combinations of effects that will explain menopause. It's hard to measure the relevant effects in the cultural and physical environments in which the trait evolved. That happened in the past, and all modern hunter-gatherer societies that we can study are disturbed to a certain extent. They're not necessarily representative of the hunter-gatherer societies that we ourselves came from in Africa, Europe, the Middle East, and Asia. So to summarize, the human life history has evolved to solve ecological problems. Our short interbirth interval is made possible by social help. We are large and fat at birth with brains that will grow for 7 more years. That brain growth requires a lot of fat. There are trade-offs between the mother's interbirth interval and offspring survival rates, physical vigor, and disease resistance in males, and reproduction and survival for females that are in poor condition. Menopause probably evolved for a combination of reasons. We listed 5 that include at least mother, grandmother, reproductive conflict, offspring quality, and self-domestication hypotheses. hypotheses. Much earlier, her age at last birth was 44 years, not that much different from Emma's actually, and her age at death was 46 years, considerably younger than Emma's. Emma is Emma Darwin, Charles Darwin's wife, and Fifi is one of Jane Goodall's chimpanzees at Gombe. If we expand that to look at the human life history and when we compare humans to the other great apes, we see that they have a rather unusual life history. These unusual features include large, fat, relatively undeveloped infants, early weaning and short interbirth intervals, slow development and extended childhood, usually one offspring, occasionally two, and menopause. We also have a life which is considerably longer than those of chimpanzees or bonobos. To see this concretely, let's take a look at two mothers. One of them is named Emma, the other is named Fifi. Emma had 10 children in 17 years. 7 of them survived, and her interbirth interval was 1.8 years. Her age at first birth was 31 years, pretty advanced. Her comparison with bonobos, chimpanzees, and gorillas. The things that really stand out are highlighted here in heavier type. Humans are heavier when they are born by almost twice the amount of bonobos and chimpanzees. They are weaned earlier. The female age at first breeding is considerably later. Age at last birth was 48 years, unusually late. Her age at death was 88 years. Fifi had 9 children in 31 years, almost the same number, but it took her much longer. 7 of them survived, as did Emma's. Her interbirth interval was 3.9 years, more than twice that of Emma's. Her age at first birth was 13 years.